Good morning, Science 9 Enriched. This is part of the enriched content during our online learning experience. So remember, if you have not completed the quizzes, and there are some of you who are still working on getting 6 out of 6 on all those quizzes, if you have not completed the quizzes, do not do this section yet. This is for enriched. This is for I've totally mastered everything else and I'm bored and I need something extra to do. Okay, so if you have not completed the quizzes, do not do this section. Go back, finish all your quizzes, get 6 out of 6 on all 4 quizzes that are out there, and then come back. And if you have time later, you can do this. If not, don't worry, this is completely optional. So if you've not completed the quizzes, do not do this. Okay. All right. Last day, we were looking at 3 different types of bonds. And all 3 types, remember we have ionic, we have covalent, and we have metallic. All 3 types of bonds are strong. Because, and see if you can think of the 2 reasons that bonds are strong. And remember, it has to do with Coulombic attraction, also known as electrostatic attraction. So why are these types of bonds so strong? It is because the distances between the charges are small. That's one reason. When the distance is small, the electrostatic attraction is big. And also, the charges are large. The charges involved are large. And remember, for this section of Science 9, a large charge is greater than or equal to 1, either plus or minus 1, okay? So if you have something that's a fractional charge, like a quarter or slightly, positive or negative, those would not be large. Now, because we have such strong bonds here, they will all require a lot of energy to break those bonds. Since they're strong, a lot of energy is required to break them. And therefore, what can you say about the melting point? The melting points are high. So that's great. We've dealt with 3 types of bonds, and all 3 of them are strong, and that means all of their melting points are high. But we know that certain things like water, its melting point isn't super high, it's 0 degrees Celsius. That's a fairly low temperature when you compare it with, say, if you wanted to melt gold or something, you're looking at heating things up to hundreds of degrees Celsius. So who are these substances that actually have low melting points? And that's where we're going to go next. We've already looked at ionic compounds. We've looked at metallic substances. And last day we had started to look at the covalent substances. And remember, a covalent bond is strong because the distance is small and the charges are large. And that is where we left off last time. And the distinction here is going to come about because there are two types of covalent substances. Okay. Number one are covalent networks. And number two are molecular substances. When we have a covalent network, the melting points are going to be high. So MP stands for melting point. But when we have a molecular substance, the melting point is going to be low. And we are going to look today at why that melting point is low, even though molecular substances contain covalent bonds, which are strong. But first, we're going to start with looking at our covalent networks. A covalent network, every atom, let's see if it says it up here, all of the atoms are attached by covalent bonds, which remember are strong, into a three-dimensional covalent network solid. Okay, and all the atoms are attached to all of their neighbors by these covalent bonds. And because these covalent bonds are strong, the melting point is high. So let's look at diamond. Diamond is an example of a covalent network. Each one of these lines in between the carbon atoms, remember diamond is an allotrope of carbon, which means it is a structural form of carbon. Okay, every single one of these lines is a covalent bond. Every single one of these bonds is strong. So you can see every atom is attached to its neighbors by very strong interactions. So that means that our melting point for diamond is going to be very high. And in fact, it is. It is super, super high. Have you ever thought about melting a diamond? How crazy hot that would have to be? Absolutely insane. Okay? Now, covalent networks are fairly rare. So we have our diamond. We also have silicon. Okay, so these were silicon atoms, and you can see the structure is really similar to diamond. The only thing that would be different is that you would have silicon atoms instead of carbon atoms, but you would still have all of these strong, strong, strong bonds in between. You might also have silicon dioxide, which is what quartz is made of. Okay, and often it is a component of sand. All right, and you can see all of these are all, again, covalent bonds. And so it's really hard. Imagine trying to melt sand, okay? You use sand to put out fires. They don't start to melt when you put it on a fire. So, yeah, these covalent solids, because all the bonds are covalent, all the bonds are strong, their melting points are high. So what is it about these other covalent substances, these molecular substances, that make their melting points low? Well, if the melting point is low, there must be weak attractions that can be broken. There must be weak attractions that can be broken. Now, if we had, say, an iodine molecule, which is made of an I and another I bonded to it, they're bonded by a covalent bond. That's not a weak bond. So there has to be something else that's going to be weak. The thing about molecules is that they are small little entities for the most part. There are long ones like DNA, but we're going to be dealing here with mostly small molecules. And if you have one iodine molecule beside a second iodine molecule, there will actually be attractive forces between those two molecules. And the attractive force between molecules is called an intermolecular force. Inter meaning between. So a force between molecules is an intermolecular force. Okay? And this force is weak. Intermolecular forces are weak. Why would a force be weak? Well, there's two reasons. It's going to be weak because the distances are what? The distance between charges is, if it's weak, the distance between charges is large. And if it's weak, that's also going to mean that the amount of charge is small. Okay? So let's take a look at these intermolecular forces. Some intermolecular forces are stronger than others. You'll learn all about the different types of intermolecular forces in grade 11. Okay, the first thing we're going to need from this is we need to know the Greek letter delta because it's a symbol we're going to use often. The Greek letter delta means slightly, okay? And it looks like this. So if you were to draw it, you would start here and go down and around and up and then a little swoop. Okay, so down, around, up, and a little swoop. Down, around, up, and a little swoop. And that is the Greek letter delta. It should look a little bit like a D. So, intermolecular forces are formed when separate, unbonded particles, okay, so we have separate, unbonded particles, and they are attracted to one another. So you can go back here and you can see, where did I draw my iodines? There they are. There is a separate molecule there, and there is a separate molecule there. They are not bonded to each other by covalent bonds or ionic bonds or metallic bonds, but there is an attraction between them. Okay, this attraction, it's due to the molecule or atom having a slightly positive end and a slightly negative end. Okay, so our slightly positive, slightly negative. And the slightly positive end of one molecule will attract the slightly negative end of a different molecule. Now, our most famous molecule, because it's used all the time in life and on Earth and sort of for all chemical reactions and things like that, is water. Water is made of an oxygen. And oxygen, you'll learn in grade 11, has a really strong pull on electrons. So even when it's covalently bonded to something like, say, hydrogen, oxygen has a tendency to pull those bonding electrons towards itself. And that will give oxygen a slightly positive charge. No, slightly negative because it's drawn the electrons, which are negative, towards itself. Because the electrons have been pulled a little bit away from the hydrogens will be slightly positive. Do you need to know how it works out that one end of water is slightly positive and one is slightly negative? No, you just need to know that you can have molecules where one end is somewhat positive, and I'm going to highlight that in yellow. Okay, so we have our slightly negative end, rather, and we're going to have our slightly negative end, which I'm going to put in, or slightly positive. I keep getting it wrong. I keep getting it backwards. Crazy me. So hydrogens are slightly positive. The oxygen is slightly negative. And if we were to have another water molecule nearby, would it arrange itself so that the oxygen, let's just draw this in here, would it arrange itself so that the oxygen is here and the hydrogens are here? Or would it arrange itself upside down to that? Think about that for a moment, pause the video. Is it going to arrange itself if it's nearby this first oxygen here? Will our second oxygen arrange itself like this, or will it be upside down? Pause for a moment and think about that. Okay, the answer is that the negative end, why do I keep saying that? The positive end will want to be near the negative end. So the positive end of that molecule, I keep saying it wrong, it's so crazy. So if I say it wrong at some point and don't catch myself, you're not going crazy, it's me who's wrong. Apparently I can't get it correct today. That green end, that positive end, is going to be attracted to slightly positive, that slightly negative end. So we're going to have an attractive force between those two, and that attractive force is the IMF, the intermolecular force. Now, when we have a molecule like this, which always the oxygen is negative and always the hydrogen is positive, slightly anyway, we call that a polar molecule. Okay, just like you have a north pole and a south pole, in this case we have a positive pole. Okay, and we have a negative pole. Which just means a positive end and a negative end. And you'll notice, just like the Earth has a north pole and a south pole, it's got different poles, this molecule has a positive pole and a negative pole, which means it has two poles. Which means this molecule has a dipole, which literally means it has two poles, positive and negative. So if something has a positive end and a negative end, we say that it has a dipole. And a dipole can be permanent. On water, it is permanent. The oxygen is always slightly negative and the hydrogen is always slightly positive. Or a little later on, it can be an instantaneous or temporary dipole. And that's a little more complicated, but we'll deal with that later. If we have a permanent dipole, we say that the molecule is polar. So this right here, where we have a positive end and a negative end, we have a permanent dipole, and so this is a polar molecule. All right, and these molecules, this is HCl here, will line up so that the slightly negative end is close to the slightly positive end. But you'll notice that the distance between those two molecules is bigger than the distance between, say, the nucleus and the shared electrons, right, which is a lot smaller. Okay. Now, if you have polar molecules, it's easy to see how you have a positive and a negative end because they're just sort of always there. This next part, just bear with me. You'll have heard about it. It confuses people, so don't worry about it too much. Basically, what we get is we have a non-polar diatomic molecule, which means that normally the electrons are randomly distributed. The electrons are here or here or here or here. There's only two of them, but you remember how we have that electron cloud where if you take a stop motion photograph, you'll see them in all different places? Normally, there's a random distribution of the electrons. They move around, but on average, they're spread out over this area. So there's not really a positive end and a negative end. But imagine that you took one photograph just at a single moment in time instead of averaged over time. So averaged over time, the electrons will look like that. But take a picture in one instant and maybe both electrons are over on the right-hand side. So in that moment when we took those pictures, this end is slightly negative and this end is slightly positive. Yeah? And if we were to take that slightly positive and slightly negative hydrogen, and if it was sitting near to another molecule with its sort of average distribution of electrons, you can imagine if there's an electron over here, it's going to be repelled by those electrons. It's going to be repelled by that slightly negative end. So what is this electron going to do? It is going to run away. Ah! Run away. Ooh. So now this molecule is going to have distorted itself. I know this is going to become like a horrible, horrible picture. Okay, so we now no longer have that electron over here. Now both electrons are over on this side, and we now have a slightly positive end here and a slightly negative end here. And if you're like, oh dear God, will I ever have to draw this? The answer is no. Okay, just realize that sometimes the electrons end up on one end of the molecule because remember, those electrons are crazy little guys, like crazy flies buzzing around, and sometimes they buzz all over to one side of the molecule, leaving the other side a little bit positive, and the side that they go to becomes a little bit negative. This can happen both in a molecule and it can also happen in an atom. Okay, so over here we have our atom. Okay, and it has gotten itself distorted because maybe its two electrons are over here. So you can imagine then if I have a helium atom, which has two electrons, and it's got its two electrons over on one side, we have a slightly negative end. And we have another helium atom over here, which has a slightly, oh God, I can't draw, that's terrible. There, that looks a little bit better. Helium, helium. The electrons have run over here. So this end is slightly negative. This end is slightly positive. This slightly negative. And this is slightly positive. We have our negative end. Here's our negative end. And we have our positive end. Oh my God, did I label it wrong? Yes, I did. That's okay, I'm going to color it because I've got my green right now. Okay, so that's positive. That's going to be positive, positive. There we go. And this end is negative. And what happens when we have a negative beside a positive? There's going to be attraction between them. Electrostatic attraction. However, look at that distance. That distance there is large. And are the charges big or are they small? Is slightly a big thing or is slightly a small thing? Well, slightly means small. So we're dealing with a small charge and we are dealing with a large distance. And if the charge is small and the distance between the charges is large, then the force is weak. And if the force is weak, it's not going to require much energy to break. So it requires little energy to break. And if that's the case, then the melting point is going to be low. All right, so when a molecular substance melts, all right, so we have, let's look at our hydrogen molecule. Here is our intermolecular force. You can imagine if I have hydrogen liquid, the temperature is going to have to be really low to have liquid hydrogen. If we have hydrogen and it's liquid, it is the IMFs, the intermolecular forces, that break when hydrogen melts. Okay, and I think I'm just going to leave it there for today, and we will come back to it again next time. Have a great day.